Hello guys, this is Rishikesh. In the previous video we saw the basics of center of mass, what is center of mass and how can we calculate the position of center of mass. We did some problem on finding the center of mass of system of particles, and we also saw the formula or the method by which we can calculate the center of mass of a continuous body. We saw that for calculation of center of mass of a continuous body, we need to do integration, unlike the system of particles where we could just do m1 x1 plus m2 x2 divided by total mass. So here in this video we will again discuss the calculation of center of mass of continuous bodies, and then we will find the center of mass of a few symmetrical continuous bodies, which is very important in terms of exams, and because we need to know how we can calculate the center of mass of such symmetrical bodies, and also we should remember the position of center of mass of those standard symmetrical bodies. So let us first start with this center of mass of uniform straight rod. So let's say that this is our uniform straight rod of mass m and length L. We know that the central mass of a continuous bodies can be calculated by using the formula. Suppose you want to find the x coordinate of center of mass, then the formula will be 1 by m integration of x into dm, where this x is the x coordinate of the differential element of mass dm, and similarly for y it will be 1 by m y dm. And see that the center of mass is going to lie on the x-axis because this rod is only along the x-axis, right? We'll ignore any height of it along this y-axis, right? So to find the center of mass, we have to first find the find the differential element. We have to select the differential element. So let's take this as a differential element of length dx, which is at a distance of x, right? So what is the mass of this dx? So the mass of the dx will be dm small m, and it will be mass per unit length of the rod, which is m by l into dx, right? And the x coordinate x coordinate of this dx will be x only, right? So let's replace it. So x will be 1 by m x x into m by l to dx. So you might be saying that uh, the x because the dx is having dx weight, the x coordinate of this will vary from here to here, but since it's very small, we can just ignore we can just take the x coordinate or as just x, and any small variations, that integration is going to automatically correct. So let us solve this one. It will become 1 by m, because m by l, m and l is constant, we can take it outside. So this will become x dx, right? So so this m will get cancelled. This will become 1 by l, and we can apply the limit of the integration from 0 to l, so that it will cover this rod completely. So 0 will be here and l will be here. So once we do that, first we'll do integration of x over dx. So it will become x square by 2, and then we'll apply the limit. So after that it will become 1 by l. We'll replace this l, it will become l square by 2, and this will become minus 0. So the answer will be l by 2. So the center of mass will lie at the center of this uniform rod, and this one we don't have to do this much calculation to find the center of mass of of this uniform straight rod, because this is uniform, and we can find just by looking at it that that the center of mass will lie at the center. So now let us take the center of mass of a second continuous body, which is uniform circular wire. So now let us take the center of mass of a uniform circular wire. So let us now find the center of mass of second body, which is uniform circular wire. So let us assume that this is our uniform circular wire, and this is our x-axis, and we will take y-axis like this one, and the origin will be at the center of the uniform circular wire. So we know that to find the center of mass, we have to first select the differential element. So let's say that we select dx here, right? Now so we know that the mass of this wire is m. So we know that to find the center of mass, the formula is for x coordinate of center of mass. The formula is 1 by m x dm, right? So if we take this as dx, what will be the dm value? We know that the dm will be mass per unit length into what is the length of this length of the semicircle will be pi r, right? Pi r. Let's say the radius is r, and then we can multiply by this dx, then this will become dm. So you might say that okay, we can integrate it from 0 to pi r, which is the total length, right? But is this the correct way? It's not the correct way, because if you do like that, then I mean integration will not know that whether we are doing the integration over this arc or just a straight line, right? So it is similar to integrating over the straight rod, which is of length pi r, right? So we have to do integration such that it covers this arc, right? So the way to do is we have to we have to take we have to find this dx, the value of dx, and then we'll integrate it over this arc, right? So if if we find the value of dx in term of this theta, then we can just integrate it over 0 to pi. Then it will know the integration will know that okay, it has to integrate over this arc, right? So let's say that we take a differential element at an angle of theta, and and the differential element makes an angle d theta at the center. Element makes an angle d theta, subtends an angle d theta at the center. Then we know that the value of dx will be r d theta. Value of dx will be r d theta, right? So now uh, we can find the dm will be m by pi r into dx, which is r d theta, right? So this r and this r will get cancelled, then this will become m by pi d theta. So so let us replace the value of dm here, and we know that x is equal to 1 by m, and this x is the coordinate of differential element, x coordinate of differential element. So we know that the value will be r cos theta, right? So we can say r cos theta into m by pi d theta, and we are going to integrate it from angle 0 to angle pi. So 0 to pi, so the x will become 1 by m. Take this constants outside, m by pi, and then we are left with r cos theta, r will also come outside. Then we are left with cos theta 0 to pi. This m and this m will get cancelled, so the value of x will be r by pi, and the integration of cos theta is sin theta, and then we'll do sin theta from 0 to pi. You know that the sin pi is 0 and sin 0 is also 0, so this will become 0. And now we will take the center of mass of, we'll find it. Now we'll try to find the y coordinate of center of mass. So center of mass, y coordinate of center of mass will be 1 by m. Similar to here, only thing that the y coordinate will be this one, which is r sin theta. So we'll just replace r sin theta into m by pi d theta. So this will become r by pi 0 to pi integration of sin theta, which is okay, because we have put integral sign, so we'll write like that, sin theta d theta. So this will become r by pi minus cos theta, which is integration of sin theta and angle 0 to pi. So this will become r by pi minus cos pi plus cos 0. So this will become, let me write this here again. So it will become r by pi into cos 0 minus cos pi, which will be, what is the value of cos pi? Cos pi value is minus 1. Then this will become 1 minus 1, which will become 2r by 2, and then this will become 2r by pi. So the center of mass value will be 0 and 2r by pi. So now we'll try to find the center of mass of a uniform circular plate. So let's say that this is our semicircular plate, and like in previous case, this is our x-axis and this is our y-axis, and the origin is at the center, and the origin is at the. So let us find the center of mass of a uniform circular plate. So let's say this is a uniform circular plate. So it has a masses here, unlike circular wire, where the masses were only distributed along the border, right? So we have to integrate in such a way, we have to select the differential element in such a that when we integrate, we cover this full circular plate. So if we just select dx like this, as in the case of circular wire, and integrate over 0 to pi, then you will only get the you will only integrate over this border, right? So we have to integrate, we have to cover this full circular plate. So what we have to do is we have to select the differential element like this one. Let's say it is of width dx, and this differential element is at the distance of r, right? But then you will find difficulty in finding the x or y coordinate, right, of this differential element, uh, because in the case of, as in the case of semicircular wire, we can just say that this is at the distance of uh, uh, from here to here is the x coordinate, right? But this is circular wire, we can't this is circular differential element, we can't just say the x coordinate of any point, right? So thing that we can replace this. We can consider this as a circular wire, um, uh, because this is of very small width, right? So we know that from the previous problem that from the previous scenario that the central mass of a uniform circular rod was, or uniform circular wire was 0 2r by pi, which means that its central mass was 2r by pi from the y-axis, right? So we can replace this uh, uh, with a point mass of which is at a distance of 2r by pi from uh, along the y-axis, right? Because the x value is 0. And then if we know that if we integrate this from 0 to capital R is is the radius of this uniform circular plate, then we'll be able to cover this full circular plate, right? So let us first find the mass of this uniform circular of this differential element. We know that the masses of the circular plate is distributed over the area. So we can say the mass per unit area is m by pi r square by 2, right? Because this is semicircular plate. And then if we multiply this by uh, the area uh, uh, of this differential element, then we can get the area of we can get the mass of the differential element. So let's say dm is equal to into uh, the area of this uh, circular area of this differential element. So we know that the area of this will be we can consider it as a kind of rectangle of length pi r into d, let's say differential element is width is dr, right? So we can say it's pi r dr. So if we calculate dm will become 2m by pi r square into pi r square into pi r dr, right? So now this pi will get cancelled, this m is total m, and then uh, uh, we also know that the this semicircular plate is symmetrical about y-axis. So we know that this central mass is going to lie on this y-axis. So we know that the value of x uh, will be 0. The value of x is going to be 0 because it's going to lie along this y-axis, right? So uh, let's say we just need to find the central mass, the location of central mass. So so in this case we have to find the y coordinate of central mass, which will be 1 by m y dm. So as we said in the beginning that we can replace uh, this uh, as a this differential element uh, with a point mass which is at a distance of 2r by pi from the origin, from the y-axis. So we can say that 1 by m integration 2r by pi into dm is 2m by 2m by r square into r dr, right? So this will become, this will get cancelled, and this m and this m will get cancelled. Then we are left with 4 by pi r square integration of r dr over the limit 0 to r. So this will become 4 by pi r square by 2 0 to r. So this will become 4 by pi r square by 2 into r square by 2. This r square will get cancelled. Then we are left with, I think I've done something wrong here. So I've done a small mistake here, not a small mistake. So because I have taken the value of y as 2 capital R, but since this is our semicircular, this is our differential element which at distance r, this should be r. So we can say 2r, and then this will become I'll have to start from scratch again. This will remain r square, and then we can just take 1 by pi outside, 1 by pi r square outside. Then this will, and this 4 will be outside. Then we are left with r square dr, and if we integrate it over 0 to r, then the value will be 4 by pi r square by 2 0 to r. Then this will become 4 by pi r square into r square by 2. Sorry, it's already r square. Then this will become r cube by 3, r cube by 3. So the value will be 4r by 3 pi. So the center of mass location will be 0 and 4r by 3 pi. This will be the location of center of mass.